Welcome to the MOOC course on Interactomics. In last lectures, we have discussed various conventional detection methods employed for protein microarrays. In today's lecture, we will discuss about various advanced detection methods. We will also talk about few methods in more detail, such as search based nanoparticles, quantum dots, dye doped nanoparticles and biobarcodes. We will first start with surface enhanced Raman scattering or search based methods. Light which is incident on an atom or molecule is scattered back with same energy and wavelength. This is a generic phenomenon. However, Raman effect prevails in a small fraction of photons, where energy of a scattered photon is different from the incident photons. Therefore, the improved optical properties are obtained because of enhanced electromagnetic field at the surface of the particle, which is detected by using spectroscopic methods such as search. The surface enhancing agents include gold and silver, as well as functionalization with target molecules which enhance the sensitivity of Raman spectroscopy. Let us now look at how the system has been employed for the detection methods for microarrays. The Raman dye labeling involves coating of antibodies on the array surface like gold by using the Raman dye directly on the gold surface, which are the nanoparticles probes. The visualization can be carried out by staining with silver enhancement solution as well as hydroquinone. The spots can be detected by Raman spectrometry coupled with fiber optic microscopy. As compared to the fluorescence based detection methods, the Raman dye labeled gold nanoprobes offer several advantages, which include high sensitivity, flexibility due to non-overlapping probes, sharp scattering peaks and cost effectiveness of the assays. However, there are certain demerits of using Raman dye labeled nanoparticles. These drawbacks include the complexity in synthesis of nanoparticles and the lack of uniformity. The macromolecular single walled nanotubes SWNTs functionalized with a specific Raman dye labeled antibodies are used for multiplexed detection target proteins bound on the microarray slide, which is gold coated. As you can see in this slide, SWNT functionalized with Raman dye labeled antibodies are used for multiplex detection of target proteins which are bound on the gold coated microarray surface. The SWNTs offer several advantages such as high sensitivity, the multiplex detection capability of proteins, minimum background signal due to sharp scattering peaks and high signal to noise ratio. They also offer resistance to photo bleaching. Therefore, SWNTs have several advantages. However, they also possess some limitations such as metal impurities during preparation of these nanotubes that can interfere with the activity. They are insoluble in biological buffers, and there is also difficulty in determining how pure your preparation is. The degree of purity is one of the major limitations here. Let us discuss gold nanoparticles, GNPs. The excitation of coherent electron oscillations that exist on interface of two materials is known as surface plasmon resonance, which forms the basis for the use of gold nanoparticles as detection system. The proportion of light absorption to a scattering depends on the size of the nanoparticle. The large nanoparticles can be used for biological imaging due to the need for high scattering cross section. The GNP labeled with a suitable captured molecules exhibit change in the emission spectrum of scattered light upon binding to the analyte of interest from a protein mixture due to specific biomolecular interactions. As you can see here in the slide, the change in the emission spectrum of scattered light directed upon binding of gold nanoparticle, which is conjugated with antibody to the analyte of interest. The gold nanoparticles offer several advantages. It has been used for several applications for sensitive detection of standard proteins. They provide improved optical property, superior quantum efficiency, show compatibility with wide range of wavelengths, and chemical stability against photobleaching. However, there are certain limitations of using GNPs, which are similar to other nanotechniques such as biocompatibility and low cellular toxicity. The systematic cytotoxicity study should be performed if you want to use these GNPs for different protein microarray based applications. The high cost, cytotoxicity, and non-uniform size and shape of the nanoparticles are some of the limitations of using GNPs as sensitive detection platform for microarray experiments. Let us now discuss quantum dots. Quantum dots are nanometer sized crystals composed of semiconductor fluorescence core coated with another semiconductor shell having large spectral band gap, which is stable light scattering or emitting properties. In quantum dots, the formation of excitons takes place when light of higher energy than that of the band gap of composing semiconductor is incident on the quantum dots. When these excitons return to their energy level, in fact low energy level, then emission of narrow symmetric energy takes place. As you can see in the slide, the change in optical properties because of the formation of excitons upon binding of quantum dot conjugated antibody to the target analyte can be used as a method for detection of microarray based method. Key advantages of quantum dots compared to the organic dyes include its brighter fluorescence, excellent photostability, multicolor fluorescent excitation and higher quantum yield. Despite its several benefits and applications in variety of biological sample, its demerits include toxicity. Therefore, quantum dots have shown various applications, but still they have certain limitations. We will talk some of these applications during the course of Interactomics modules. Changes in the emission wavelength upon binding to the antibody conjugated quantum dots are recorded by the microchip and used for detection of various biomolecules. Quantum dots are capable of detecting molecules down to femtomolar levels and provide significant advantages over conventionally used organic fluorophores. In this interaction, we will see how quantum dots work. The inorganic fluorophores known as quantum dots have been developed that can conjugate with several biomolecules and be used for protein microarrays signal detection. They are made up of semiconductor devices which form excitons upon absorption of light. There is emission of a narrow energy band when these excitons are returned to their lower energy level. Let us click on these quantum dots to view how they work. So, as you can see, upon binding of the target protein to the antibody, now these changes are plotted on the wavelength versus fluorescence intensity graph. So, these quantum dots can detect molecules with very high sensitivity in femtomolar range. Now, let us discuss about dye doped silica nanoparticles. The silica based nanomaterial have large quantity of fluorescent dye packed inside the silica matrix, which possess ability to selectively tag a wide variety of biologically important targets such as cancer cells, bacteria and many other biological samples. As shown in this slide here, the silica based nanoparticles have large quantity of fluorescent dye packed inside the matrix, and it can be used for selectively labeling of protein molecules for detection of biomolecular interactions. Dye doped silica nanoparticles applications have been used for a variety of investigations. Application of various functionalized silicon nanoparticles have been demonstrated in diversified fields such as biomarker discovery, drug delivery, multiplex signaling in biomolecules. Its various merits include biocompatibility, high sensitivity, minimal aggregation and dye leakage, photostability and high capacity. The demerits of dye-doped silicon nanoparticles include its complex synthesis process. We will now talk about biobarcodes. The nanoparticle probes encoded with DNA unique to the protein of interest and suitable antibodies capture the magnetic microparticle probes known as MMPs having antibodies for the target analytes, thereby sandwiching the target proteins, which is shown in this slide. These are magnetically separated oligonucleotides dehybridized and then sequenced to identify the protein of interest. The nanoparticle based biobarcode have increased the detection limits down to attomolar range. The liberated oligonucleotide barcodes can be identified on microarray surface by scanometric detection as well as using conventional fluorophores. The nanoparticle based biobarcodes offer various advantages. The merits include high sensitivity, less detection time, and it can be easily adapted to multiple protein targets. The demerit of this method is that it can only be used with known antibodies. Therefore, the number of antibodies as well as good quality of antibodies is one of the limiting factor for performing the nanoparticle based biobarcode assays. In fact, the same is also true for many applications in proteomics which also require antibodies. To summarize all the various type of detection techniques which we have discussed today, the advancement in the microarray technology have led to the development of sensitive and reliable detection systems. There are different label based detection techniques which have been employed to study high throughput ways of analyzing thousands of proteins as well as studying their interactions and function by using protein microarray platform. These various novel detection techniques which we have discussed today have facilitated sensitive, specific, high throughput as well as rapid analysis for many proteomics based applications. The label based detection systems have been taken rapid strides to satisfy demands of proteomic applications with significant improvement in sensitivity, multiplexing capability and reproducibility. So, we have discussed variety of label based methods, although Fluorescence based method is one of the most commonly used method for various protein microarray based application, but there is an increasing demand and need to try out new levels so that one could achieve ideal system which can be applied for microarrays and also provide good detection system with high specificity, sensitivity and large dynamic range. So, we have until now discussed various traditional and novel detection techniques used in protein microarrays. In next lecture, we will talk about recombinational cloning and its application in protein microarrays. Thank you.